Hey everyone, in this video we're going to continue talking about area under a curve. This is part 2, and just to summarize, based on the first video we had talked about that to find the area under a curve on the interval from A to B, we can use a number of rectangles and try to approximate the area by adding up the areas of each of those rectangles. So if you have n rectangles, it will be a1 plus a2 plus all the way to your last rectangle, a sub n. And remember, the area of a rectangle is base times height, or length times width. In this context, base times height seems a little bit better because we can think of the base as right on the x-axis, and then the height is the height of the rectangle, which is on the curve. And so the height of the rectangle depends what you're using, whether you're using left endpoint, right endpoint, or the midpoint. So I'm just going to say the height depends on the endpoint. So when you break up your number line into the subintervals, then you're looking at what am I using, the left endpoint for the height, am I using the right endpoint for the height, or am I going to be using the midpoint? And so then what we found last time was that delta x then is the length of the interval, so b minus a divided by the number of rectangles that you want, and so that allows you to break it into equal parts for n rectangles. And so then the area is approximately, so the area for the first rectangle, a1, will be the base, so delta x times f of x1, and so on. For the second rectangle, delta x times f of x2 plus the third rectangle, delta x, f of x3, and so on until you get to your nth rectangle. So the area of the nth one will be delta x times f of x sub n. And so and from here we can factor out the delta x. So it'll be delta x times, and then you can think of the sum of this. And we can bring in the more formal notation, and so we can say A is approximately, so the area is the sum of all of these. So the sum of, and we can say from I equals, so this is our counter, 1 to n, because you have n rectangles, of delta x of I times f of x sub I. So this is our counter, right? So if we start with I equals 1, then you'll have delta x. So all of these, I guess I don't need the sub I over here because they're all delta x. Sometimes the length changes, but not in our case. So it's just delta x, f of x sub I. So for the first rectangle, so I is 1, you're going to have delta x times f of x of 1. So that will be this one, a1. And then you move on when I is 2, it will be delta x times f of x of 2. So that will be this one, your second rectangle, and so on. When you get to n, the sigma means you're adding them, so you plus plus plus. When you get to n, this will be the area of your nth rectangle, so f of x sub n. And this is the way I have written this formula, as if I was using the right endpoint. And so what you'll oftentimes see instead is that we'll have I equals 1 to n of delta x times f of x sub I star. And the x of I star just then allows you to choose what endpoint you're using. So where x of I star is either your left endpoint or the right endpoint or the midpoint. Of each subinterval. What do I mean by subintervals? Right, our big interval is A to B, so that's the interval. The subintervals are these little ones from A to x1, x2, x3, and so on. So that's what this is. So x of I star then refers to which endpoint are you using to find the height of the rectangle. Are we using the left endpoint, or are you using the right endpoint, or are you using the midpoint? But the general format would say x of I star in order to find it, to find the area. So this is the thing to remember. Sometimes with the summation notation, it may be confusing for some people, so you can just remember this, that is delta x times and then the f of, and then your different heights, right? The subinterval, which one are you using, left endpoint, right endpoint, or midpoint? So let's do our next example. So our example is we want to approximate the area under the curve and the x-axis on the interval from 0 to pi with 6 rectangles using all 3 endpoints. I'm going to use this example to illustrate the different, how it looks when you use the different endpoints. And our function is 2 plus sine x. So let's go ahead and take a look at what the function looks like first, and let's then find our subintervals. So because we have f of x equals 2 plus sine x, now remember, if I just had y equals sine x, this will look like it starts at 0, 0, and it goes up all the way to 1, down to -1, and it ends at 2 pi. So we're graphing it between 0 and pi, and it is up to, because we have the plus 2, so it's going to go up here, up to 2. So normally our middle line here, the 0 line, is now at 2, and we're going to go just between 0 and pi, so it's going to be this part of the graph, but up from 2 to pi. So let's graph that real quick. The amplitude is still 1, right? It's 2 plus 1 sine x, so it's just going to go from 2 to 3. So this is where the highest point of sine is. And it says using 6 rectangles. So what is our delta x going to be? So delta x is 6 rectangles, so that means we're going to have 6 subintervals of equal length. So we can say then delta x is b minus a, so pi minus 0 over the number of rectangles, the number of subintervals, so 6. So our delta x is then pi over 6. And so now we can break up the interval. So we want 6 equal pieces. So let's see, 1, 2, 3, 4, 5. Pretend those are equal. And so we can start putting them in. So the first one then is pi over 6. And then how do you get to the next one? Add pi over 6 until you get all the way to pi. So pi over 6 plus, remember, because this is, each of them is pi over 6. So that's why I'm saying add another pi over 6, because essentially to get from this one to this one, you need to add another pi over 6. So it'll be 2 pi over 6, which is really pi over 3. And then, so add another pi over 6, so that'll be 3 pi over 6, which is really, what, pi over 2. And then 4 pi over 6, which is 2 pi over 3. And then 5 pi over 6, which does not reduce. And then 6 pi over 6, which is pi. And so those are this is our subinterval. Now, for the first part, it tells us that we want to use right endpoints. So the right endpoints are going to give us the height of our rectangles. So when I'm looking at my first subinterval, right, this is the interval 0 to pi over 6. So when I'm looking at the right endpoint, and so that will be this one. So this is the right endpoint. So that's when what I'm going to look for in the height. And so when I'm looking at so that's the first one, so 1, 2, 3, 4, 5. So if I'm looking at this one for A5, right, this interval is the interval 2 pi over 3 to 5 pi over 6. Which one is the right endpoint? The right endpoint is the 5 pi over 6. So that's the one I'm going to be looking at to find the height. And then A6, well, I'm going to be looking at pi. So when we talk about the left endpoint and the right endpoint, we're looking at the tiny little subintervals that we created, and then looking at, okay, right endpoint. So we're always looking at the one on the right. When we move to the left endpoint, now we're going to be looking at the subinterval, and we're going to be looking at the one on the left. So 0 in this case, and then 2 pi over 3 in this case. Okay, so let's see what our rectangles look like with right endpoints. So here are our rectangles drawn with right endpoints, right? So notice that the subintervals, the endpoint on the right is the one that I'm using for the height of the rectangle. And so those are the ones that I've highlighted. And so notice in this case, because the way that the graph moves, here we have a little over approximation, but then here we have under approximation. So this is a really interesting one. It will be interesting to know what the actual area is, and then we can compare our approximation to the actual area, but we'll get to that in the next few sections. So here for the area, now let's remember that our function, what was our function? Our function is 2 plus sine x. So our formula for the area is that we want to do our delta x times then f of x of I, and we're using the right endpoint. And so we're going to take a look at our function here. And so the area is going to be the area of the first rectangle, and the second added with all the other ones. You should have 6 rectangles, which we do. And so I can now say, so our delta x we said was b minus a over n, which in our case is pi minus 0 over 6, which is pi over 6. This is what allowed us to break up our interval. It's really important to use your delta x to figure out your subintervals. That's probably like the key step to approximating the areas under the curve. So now we can say, okay, so it's going to be delta x, so pi over 6 times, and then because I'm going to factor it out already, because we said over here in this one that we can factor it out, and then just have the sum of the heights using the right endpoint. And then we'll do it again for the left, and we'll do it again for the midpoint. So here we're going to have f of the first one. So our first endpoint will be the right endpoint, pi over 6. So it'll be f of pi over 6 plus then the next one, f of pi over 3 plus f of pi over 2. So all the ones where I have a highlight, those are my heights. And so the only one, notice that's not highlighted, essentially is 0, but that's because that we're going to use 0 when we're doing the left endpoints. So where am I? Pi over 2 plus f of 2 pi over 3. I'm probably writing too big. So these are our 6 right endpoints plugged in, and now we plug them into the function. So we're going to have the area is approximately our delta x times f of pi over 6. Now remember, our f is 2 plus sine x, so what's f of pi over 6 going to be? That's going to be 2 plus sine of pi over 6. So I'm going to put that in here. So it'll be 2 plus sine of pi over 6, and then you do the same thing for all the other ones. So 2 plus sine of pi over 3 plus 2 plus sine of pi over 2, and so on all the way until we get to pi. And now we evaluate our trig function or sines. So the area is approximately, right, always put approximately because this is just an area approximation. We're using 6 rectangles to approximate the area. We don't have the actual area under the curve just yet, but that's coming. So sine of pi over 6, what's sine of pi over 6? 1/2, right? So then you're going to have 1/2 plus 2 plus sine of pi over 3, then that must be root 3 over 2, plus 2 plus sine of pi over 2, that's 1, plus 2 plus sine of 2 pi over 3, that's root 3 over 2 again, and then 2 plus sine of 5 pi over 6, that's 1/2 again, and then plus 2 plus sine of pi is 0. And combine whatever like terms you can combine. So let's see, what can we combine? We can combine, so that's 2, 4, 6, 8, 10, 12. Makes sense because we were adding it 6 times. So 12 plus, and then you have your 1/2. How many times does that show up? We had 1/2 plus another 1/2 here. So that will be plus 1. Oh, there's a 1 there. So let's do plus 1 plus the other 1. So this 1 comes from the 2 1/2s. What's a better way to do this? Maybe just highlight it. That 1/2 plus that 1/2 gives us that 1. And then this one is this one. And then we have root 3 over 2 plus root 3 over 2. So we can say that is 2 root 3 over 2, which then will just be root 3. And so this becomes pi over 6 times, what's that, 14 plus root 3. And you can put this on a calculator and get the decimal answer. Which when we put it in our calculator, we get, I got 8.237. So if you're doing this on homework, just be mindful, pay attention, how many decimals are you being asked. So if it's 3 decimal places, this will be it. If it was 2 decimal places, it will be 8.24, and so on. So this will be our approximation for the area under the curve y equals 2 plus sine x on intervals 0 to pi, using right endpoints. So now let's take a look at using left endpoints. So what does our how does our area change using the left endpoints? So let's make a picture of that and then find the approximation. So here we have now the graph with the left endpoints. So when we break up our function or interval or big interval, right, we did it over here. You have your graph, the interval is from 0 to pi, and we find our delta x, which was pi over 6, so you break up your interval. So this is going to be where your rectangles are, 6 rectangles. And then using right endpoints, we draw the rectangle with the right endpoint being the height. And so now we're moving on to left endpoint. So we draw our rectangles with the left endpoint being the height. So notice that our first subinterval here is the interval 0 to pi over 6. So using the left endpoint is going to give us the height. So when I do the area, then my area is going to be approximately delta x, so pi over 6 times then f of, for each of these rectangles, right, this is my A1, A2, A3, A4, and so on. So, but now the height is given by the left endpoint, so it will be f of 0 plus f of pi over 6. So the next subinterval is the interval pi over 6 to pi over 3, but I'm using the left endpoint. So plus f of pi over 6 plus f of pi over 3 plus f of pi over 2, f of, what's next, 2 pi over 3, and then, so that is my A5. So now notice for A6, my sixth rectangle, what's the interval? The interval is 5 pi over 6 and pi, but I'm using, so this is my last rectangle, but the left endpoint is what I'm using, so it'll be f of 5 pi over 6, and that is it. So this will be, so let's make sure we have 6 rectangles, right? Base times height. So I should have 6 heights. 1, 2, 3, 4, 5, 6. So we're good. And so now we find this value. So I evaluate it the same as we did before. So that will be 2 plus sine of 0 plus 2 plus sine of pi over 6. And a lot of these we already found their values. And so we put in our values. Sine of 0 is 0, right? So we're going to have 2 plus 0 plus 2 plus sine of pi over 6. We already saw that that's 1/2 plus 2 plus root 3 over 2 plus 2 plus 1. Sine of pi over 2 is 1 plus 2 plus sine of 5 pi over 6, which is, oh, did I skip one? I skipped the 2 pi over 3. There should be a plus 2 plus sine of 2 pi over 3. Root 3 over 2, and then plus 2 plus 1/2. And so what do we get? So same as we did before, combine the ones that are like terms and simplify as much as you can. So I'm going to do that in one step. So what do we get when we simplify everything? And notice that we get the exact same thing. This is the 8.237. So why is that? This is not usually the case. And the reason that this is the case is because sine is symmetric on 0 and 2 pi. So notice that the values are the same. So even if I use the left endpoint, the height here is 2 because sine of 0 is 0. But when we go to pi, the height is still 2 because sine of pi is 0. So you have 2 plus 0 again, and then this is nice and symmetric, so that's why for the left and the right endpoint we get the same thing. But normally they will be different if you don't have a symmetric graph. So because of symmetry, notice that then how the area looks. So here we have on the left side of pi over 2, right at the beginning we have an under approximation, and then it moves to an over approximation. Whereas when we were doing the right endpoints, we started with the over approximation first and then the under approximations. And so that's just, we can see the symmetry here, and I can see how the right endpoint and the left endpoints are going to be the same. So now what about the midpoint? So using midpoints means that the midpoint of each subinterval is what's giving us the height of the rectangle. So this is what gives the height. So how do you find the midpoint of each subinterval? So let's look at the first subinterval. So I'm looking at between 0 and pi over 6. So what's the midpoint there? How do you find the midpoint? You add the two coordinates, so 0 plus pi over 6, and you divide by 2, right? So then this will be pi over 12. So this one is pi over 12. What about the midpoint between pi over 6 and pi over 3? So midpoint on pi over 6 and pi over 3, sorry. Then this will be same thing, midpoint, you add the 2, so it'll be pi over 6 plus pi over 3, and you divide by 2. So what is that? You need a common denominator of 2, right? So that'll be 2 times 2 on the top and 2 on the bottom to get the 6 there. So common denominator 6 on the numerator. So that'll be 2 pi over 6 plus pi over 6. So that's 3 pi over 6, and then divided by 12. So that means you have 3 pi over 12, which reduces to pi over 4, and so on. So you go through and find the midpoint of all of these. So you can see that probably the midpoint is not gonna be our favorite one to use, because it requires us to do more math, and it's just makes the process longer, right? And this is with 6 rectangles. Imagine if you had to do it with 12 rectangles, and you have to find the midpoint then of those 12 little subintervals. So sometimes you can kind of start seeing a pattern, right? Because this is pi over 12, and this one, before we reduced it, we said it was 3 pi over 12. So I can put that there to 3 pi over 12, which is really pi over 4. But notice that then it will go pi over 12, 2 pi over 12 as pi over 6, then 3 pi over 12, so 4 pi over 12. So then this must be 5 pi over 12, then 6 pi over 12, then 7 pi over 12. So you can kind of start seeing a pattern. 8 pi, so 9 pi over 12, and then 10 pi over 12, so that must be 11 pi over 12. And so you get to then pi is 12 pi over 12. So everything should come out just fine. So then the red ones are the ones that we're going to use as our endpoints for the height. So let me then get rid of that one, because that one is red, but I don't want to confuse you. So then our area is going to be approximately our delta x, which is still pi over 6, times, now we're going to do f of, we're using the midpoints. So our first midpoint is pi over 12. So f of pi over 12 plus then f of 3 pi over 12, which is pi over 4, plus f of 5 pi over 12, and then 7 pi over 12, 9 pi over 12, and our last one, f of 11 pi over 12. Do we have 6? 1, 2, 3, 4, 5, 6. Good. We have 6 rectangles. We already factored out the base, right? The area of each rectangle is base times height, but we factored out the base, but we have 6 rectangles. Factor out the base, we should have 6 heights. And so that's one way to kind of quickly check, did you get them all? If you have an extra one, okay, then which one is your extra one? If you are missing one, which one are you missing? And then plug it into your function. I guess I should have done that down here. Let me copy it. And recall that our function was, our f of x was 2 plus sine x, and so that's what you would put in. So our area then will be approximately our pi over 6 that we have on the outside times f of pi over 12, so 2 plus sine of pi over 12. We'll definitely need our calculator for this one, plus 2 plus sine of pi over 4 plus f of, oops, not f of, 2 plus sine of, and the next one, so 2 plus sine of 5 pi over 12, and you kind of get the point here. So complete all 6 and put in your calculator to evaluate. When I put this on my calculator, I got 8.306, rounding to 3 decimal places. So let's compare our answers. Well, we already saw that with the left and right endpoints, we got the same due to symmetry, so it's 8.237. And then with the midpoint, we get 8.306. And so those are pretty close, 8.306 and 8.237, well, somewhat close. They would be nice to know what the actual area is. You will be able to do this later, but the actual area is 2 plus 2 pi, which ends up being 9.28. So now keep in mind here, we're only using 6 rectangles. If I use 8 rectangles, that would already put me closer to this, to the 9.28, the actual area. If I use 12 rectangles, even closer. So what we're working towards here is that the more rectangles you have, the better approximation you get, the closer to the area we're going to get. To eventually say, what if you had infinitely many rectangles? If I had infinitely many rectangles in here, then I will actually have the entire area under the curve. And so that's what we're going to be working towards, being able to set up areas under the curve using rectangles, either right endpoint, left endpoint, or midpoint. And then what does the limit go to as n goes to infinity, as the number of rectangles approach infinity? What is the value of that limit? And that's what's going to give us the actual value of the area under the curve. So this is a stepping stone into being able to get there, to find the actual area. All right, so just to bring you back, way back from the first video, we were able to find the area under the curve, and in this case the curve was just a line, and the area under the curve represented on that interval, it was just a triangle, which we can use geometry to find that. But when we have something else, something that is not a known geometric shape, how do we find the area that represents? And so our goal is going to be to just be able to find the area without having to do the approximation. So we start the approximation by seeing, okay, the more rectangles I use, the better my approximation. So the idea is when I have infinitely many rectangles, so the limit as n goes to infinity, as the number of rectangles go to infinity, what is the numerical value? That's going to be our area, our actual area under the curve. And so that's what's coming. So that's what we'll be working in the next couple of weeks. All right, email me if you have any questions.